science, sir, you got to know I'm going to invite you, obviously, this was for you. But ladies and gentlemen, with a round of applause, please welcome Shri Shivanand Kanvi amongst us. Thank you so much for joining us, sir. I would request you to kindly be here between the stage. Besides science, technology, and Indian industry, his interests include political economy, Indian history, darshana, philosophy, S&T communication. He continues to contribute frequently to Business India, Prajavani, Kannada, Rediff.com, and Gadar Jari Hai. Shri Shivanand Kanvi sir has had a varied career after academic work and teaching in the year 1972 to 84. He in theoretical physics at IIT Kanpur, Northeastern University, Boston, IIT Bombay, and Bombay University. Shri Shivanand sir became an economic consultant in the year 1984 to 1991 and later turned to business journalism. He was executive editor of Business India in a pioneering business magazine 1992 to 2004. Finally, he worked in the corporate sector as vice president in TCS 2004 to 2013, the largest IT service company in India, perhaps in the world. He has widely traveled in India, US, Canada, Mexico, UK, France, Germany, China, Japan, Italy, Poland, Kazakhstan, Taiwan, Singapore, and so many more countries. I'm sure how many passports have you been stamped, sir? Shri Shivanand Kanvi sir has authored a highly claimed book, Sand to Silicon, the amazing story of digital technology, Tata McGraw-Hill 2004 and Rupa & Co. in 2006. It is for the first time the evolution of digital technology and highlighted Indian contribution in semiconductors, microelectronics, laser, fiber optics, telecom, commuting, and the internet. The book was highly appreciated by leading scientists and technologists across the world, including former President of India, APJ Abdul Kalam, Dr. Kasturi Ranga Sir, Anil Kohalkar, FC Kohli, Dr. R.A. Mashilkar, Dr. Deshpande, Dr. Clinton Christensen, Yashoro Masamota, and others. The book has been translated into Kannada and published by the government of Karnataka in 2016. To research for the book, he interviewed over 200 top technologists in Stanford, Harvard, MIT, Yale, UNIV of Michigan, Ann Arbor, and Universities of Illinois, Caltech, UC Berkeley, Princeton, TIFR, IITs, IIS, and as well as Bell Labs. He has edited a book highlighting TCS strengths in strategic innovation and R&D research by Design Innovation and TCS, Rupa & Co. 2007. Ladies and gentlemen, Shri Shivanand Kanvi sir is Shivanand in one of the most acknowledgeable writers of Indian IT manufacturing, nuclear and space programs. He has been widely quoted in Indian international press as a subject expert. His current interests include Indian philosophy, history, and political economy. He was awarded the Madhu Valluri Award for Journalism for the year 2004. Indeed, it's a pleasure to have you, sir. Thank you so much for joining the Entrepreneurship, Business Design, and Startup Awards 2022. With a round of applause, ladies and gentlemen, kindly welcome Shri Shivanand Kanvi, sir, amongst us.
Thank you.
Sir?
Yes. Yeah, thanks. Well, after that song and dance of CV, let's come down to earth. We have already been introduced to multiple universes. I mean, I had heard about it in quantum physics. We used to talk about, there was a theory of multi-universes, parallel universes, and so on. But now Facebook and Meta are creating this metaverse, and Abhishek has introduced us to it. and we have had the privilege of listening to Mr. Raghu, who brought us, who started from the earth, very much earthy discussion of finance and how financial discipline, etc. And Dr. Ajay introduced us to architecture and startups and you know, the whole ecosystem that is required for it. And Mr. Timaya, of course, took us to the elements, you know, you can say Panchamahabhuta, you know, Prithvi, Ap, Teja, Vayu, Akasha, all five he introduced, that how we have to live with them, and only by living in harmony with them that we can survive and grow. And if we take panga with any of them, then we'll be in trouble, both as individual human beings and as a civilization. And we are going to listen to Professor Jaisim now. Now, what I want to talk about is, as a techie, how do I look at entrepreneurship? And also, since the subject says design, so I want to give my 2 cents worth on design, which I think initially I had great hesitation, because design conjures up a very, you know, subjective, artistic, aesthetic aspects of our life, and which definitely natural science and engineering and technology goes the exact opposite of that, which is quantitative and you know, and so on. But still, I try to grapple with what design means to a techie, and I'll give a few of my thoughts on that. To begin with, entrepreneurship as a techie is, see, there are all kinds of entrepreneurship, right? Everybody, in fact, somebody said it some time back, forgot the name of the book, famous book, that every farmer is an entrepreneur, right? He is taking risk. He's doing something for which he may or may not get a result 6 months later. He has to deal with elements, right? He has to live with them, and despite that, despite the elements, he is to make a guesstimate on what he is going to get in return for the labor today. In fact, there are theories which say that poetry and all these things evolved out of these primitive agricultural communities. You know, to create an imaginary world of harvest when you are actually digging the earth, you know, and trying to sow your seeds and you know, sweating away, and you can only do it as an individual and as a family or as a village only if you are fired by the dream of the harvest, which is going to come several months later. And that's how poetry emerged, and that's how magic emerged, and from that science also emerged. This is one of the interesting theories, anthropological theories. Anyway, so there are entrepreneurships of all kinds. Now I want to talk about recent digital entrepreneurship, and in which Indians have done remarkably well, contributed remarkably well. And something which I researched about quite in depth initially around the year 2000, when the dot-com boom was going on. I was working in Business India, and 4 of us were sent to US to spend a month and travel all across to find successful Indian entrepreneurs. And those days, a couple of names were known: Sabir Bhatia, Vinod Khosla, or Kanwal Rekhi, or some 2-3 names were known. And B.V. Jagdish and K.B. Chandrasekhar were just coming up at that time. And we came up with profiles of at least 70 of them, and produced a special issue, 200-page special issue of Business India, whose title was "How High-Tech Indians Won the Silicon Valley." And it was greatly appreciated all over the world. And then later, I proposed to the Tatas, I was still working in Business India, a project on what Indians have done to the fundamentals of technology, of digital technology. Okay, not in terms of net worth, because you know when there's a boom in the market, you become a billionaire. When there's a crash, it's very fast, you become a millionaire, or from a millionaire you become a pauper also. So the net worth calculations don't mean much if when you look at the fundamental contributions to technology. So the Tatas, with a fine comb, they fine tooth comb, they actually examined my project, and they found it interesting, as they thought that research on this had not been done, and if you can do it and then convey to the lay public, then that will be very inspirational to the young Indians. So they took it up as a part of the Tata Centenary in 2004, and I spent about 14 months. I took a sabbatical from Business India and worked on it, and as she mentioned, traveled all over and interviewed literally hundreds of techies in India and in Canada and US and so on, and was able to come up with a reasonably coherent story of how actually digital technology evolved from the birth of the transistor in 1940s, and then how it has evolved in all these aspects, and what Indians have done in that, and what probable consequences of this technology will be to India, because in the early 2000 it was not obvious how it will change India. Because what happens in Silicon Valley is something else, and what will happen in the villages of India, in the tribal communities of India, in the cities of India is something else, or to the farmers of India. So now, of course, it is very easy to talk about the digital revolution because we actually are living through it. Okay, so I'll just look at a few of these contributions. We have a very limited time. I think another 15 or 20 minutes. That's about it. So let me zip through it, and if there is I'll try to make that. You will probably see a bit of text on the slides, which I am sure as designers and architects you will hate. There are not many pictures, but if there is a little time, I'll show you some pictures also and raise some questions. Okay, these are some of the important ideas, the ideas which were transformed the world. And when I say the world, see, don't be hesitant to declare that an idea or a project that you do in India can transform the world in claiming that. Because once when I was in TCS, I was looking at one project and talking to a good team which was doing a project, and it was a very good project which they had done for Northern Ireland. Okay, and then the government of Northern Ireland was very happy with it. Then I looked at the population of Northern Ireland. Okay, it is less than the average population of a district in India. You have 1.4 billion people, 1400 million people, and 600 districts. Okay, so at least 2 million people per district. And so the population of a district in India is equal to more than number of nations in the world. So if your project or your idea can change the life or touch the life of a district in India, you can claim it is a global project, global size project. Forget about the entire India. Okay, so that's why I said it. The transformative ideas that change the world and not just India. Okay, the first one is TIFRAC, that is Tata Institute of Fundamental Research Advanced Computer. This was a project which Homi Bhabha wanted to build a digital computer. There was no digital computer in India. There are hardly a handful of digital computers in the world. One was in Princeton, which was built by von Neumann, who was the founder of computer science, and which was basically being used initially for the atomic bomb project. And that was about it, and there was one in the University of Illinois, and that was it. So, and he called Professor Narasimhan, who was a mathematician, who had never seen who had just used a computer, didn't know anything about electronics, and he said, build a digital computer. So Professor Narasimhan took up that project, and with 3-4 other people who had never even seen a computer. At least Professor Narasimhan, during his PhD in the US, he had seen a computer and used it for calculations. Okay, and they went ahead and built the first digital computer in India in 1954. That was TIFRAC. So if you look at the birth and development of computer science in India, that was a major thing which changed, you can say, the technology scenario when there was no electronics in India. There are hardly any transistor. Transistor meant a radio in which you could probably listen to some Vivid Bharati or Radio Ceylon or something like that. Okay, and there are no chips. There is no chips anywhere in the world. Also, chips were discovered in the late '59 in Texas Instruments by Jack Kilby, and later developed by Intel and so on in the 60s and 70s. Right? And only electronics knowledge was in little bit in AIR. There was no Doordarshan at that time. And Bell. Okay, at that time to build a digital computer, and in fact in 1954, which was as good as any other computer in the world. So that was a transformative idea, and which not only an idea, a dream, which actually they actualized. Next is SITE. SITE is satellite instructional television experiment. Okay, this is a different type of real estate. This is a real estate in space, you can say, when you talk about sites, right? So this was done in Ahmedabad in the late 60s, in the satellite applications, which became Satellite Application Center and so on. As a result of that, that was an experiment that how you can use a satellite and you send a signal from here, which can mean a program, an educational program or any such thing, and that can be received down from the satellite somewhere else, okay, and then that can be channeled to a local TV. That's all. It had not been done anywhere else in the world. After all, television was a terrestrial television all over the world at that time. So for the first time, satellites were used for television broadcasting as an experiment. And a tribal village in Madhya Pradesh was linked to the studio in Ahmedabad where some lessons were being broadcast, and through this satellite. That was ISRO's experiment in SITE, which it is that knowledge, that techniques which were developed, is what led to proliferation of television and later color television all over India. When you saw the Asian Games in 1980, when the color broadcasting started and so on, and then very quickly it covered the entire length and breadth of India, it was because of satellite technology and not terrestrial technology. Okay, and that came out of SITE. So whether it is entertainment or infotainment or telemedicine or teleeducation or distant education, all that we talk about now in the age of internet was actually initiated by by ISRO with the SITE experiment in the late 60s. Then came CDOT of Sam Pitroda. When you heard all this, I don't know, I mean, looking at your faces, I don't think you've ever seen that trunk call and going to a post office and booking a trunk call and all that, except for the speakers here who belong to my generation. In that situation, when we had old technology, analog technology, how do you build a digital telecom system? Okay, and what was being offered by the telecom giants of the West was very, very expensive. India could not afford it. At that time, an Indian entrepreneur and a techie called Sam Pitroda, who had developed some digital switches in the US while working in the US, approached Mrs. Indira Gandhi, don't confuse it with other Gandhis now, and at that time, and gave her a presentation on how we can modernize Indian telecom, and for that, with indigenous efforts, we can build the digital electronic switches that are required for it, instead of buying them from the Western ones. And at that time, Mrs. Gandhi even got letters from some of the CEOs of the Western telecom companies saying that we have spent billions of dollars in this research, you will not be able to do it, forget about it, you just buy the switches from us and digitize it, we'll give you the entire infrastructure, backup equipment and all that. But unfortunately, Mrs. Gandhi passed away very soon after that, and then Rajiv Gandhi, who was also at that time a young MP who was sitting in that presentation, continued that association with Sam Pitroda later when he became Prime Minister and encouraged him, and Sam Pitroda established this first Center for Telematics. And this Center for Development of Telematics, which was established, was a new thing. Though it was a government organization, it was totally autonomous. He was given free hand to recruit young people and give them all sorts of freedom, which today are routine in any startup, right? But in a government organization, that too in the 80s, was unthinkable. Where for everything you need to pass through so many tables and so much bureaucratic work. But very soon CDOT came up with a switch, and today that switch, not only it revolutionized Indian telecom and made it digital, but it has revolutionized digital telephony across the world. It's the most widely used switch in the world. Almost all the countries in Asia, Africa and Latin America have bought those switches to digitize their telecom, the landline telecom. Okay, so it's the most widely used switch even today, what is considered as a village telephony switch. But that was the basis of the telecom revolution. Okay, for the first time we had digital, first time subscriber trunk dialing came in, what is called STD, you just dial and there is a code given and you reach another landline, right? But at the same time, that time India had very few telephones. So how do we now suddenly modernize the telecom where, for hundreds of millions of people we provide telephones? How can we do it? Can we lay the cables? Can we lay the copper cables? Because the fiber optics and that telephony had not yet come in big way in the world. It was just beginning in the West. So we could not yet afford it at that time. It was still copper cables. So how can you lay so much of copper cables and switches and exchanges and so on to bring telephony? Because it was clear that just the modernization of telecom can add anywhere between 2 to 4% to our GDP growth. Okay, so at that time the idea came that why should we follow the Western model that everybody should have a telephone in their house? What we want is not telephone ownership but access to telephone. Okay, there is a big difference. When you measure teledensity, normally you talk about how many telephones per 1,000 people, but all you needed was one telephone booth called STD booth in a village. The entire village could use it, right? Sharing, this is what is called sharing, and our culture is used to sharing. After all, every commuter in a train or a bus knows if he has got a newspaper in his hand, before he has even finished the first page, then his neighbor wants the last page or the middle page and so on, right? We are a very, very sharing culture. We are not necessarily ownership driven culture, that this is my paper, this is my towel. Even in the house, it is very recently that you have one bedroom for one person and so on and so forth. Architects know it very well, right? So the STD booth revolutionized, and already mass migration had started in India. So you could have a laborer far away from his hometown call up his home just using the STD booth. So it revolutionized so many things, and made life simpler. It helped business and it helped ordinary people. Another idea, this is in computing. Today we talk about supercomputing, right? In how many teraflops and petaflops and all that. There's a big race going on, and China and United States, and they are in the race. India also says that we also built. But what is the what is the nature of these supercomputers? So there is one type of supercomputer which was built by Cray computers, which had a particular type of architecture, but those computers needed such high, they produced so much heat that you needed liquid nitrogen to cool the computer. Okay, minus 78 degrees centigrade, something like that, you needed that kind of cooling to run those computers. And you needed those computers for fast computing for many things. Basically, it had defense applications to simulate a hydrogen bomb, what will happen when you design a hydrogen bomb, or what is the dynamics of a fighter plane, and so on and so forth. But they were also used for weather prediction. Okay, so when India said that for weather prediction we want it, the US was not interested in selling any of those computers to us, or any fast computer at that time. Okay, so at that time, a scientist in National Aeronautics Laboratory, Radham Narasimha, who, he said, I need to do some calculations for aerodynamic calculations, and what I can do is I can take simple microprocessors which were available there at that time in the late 80s, and make a parallel computer out of it. Okay, I take 100 of them, I network in such a way that it is as good as 100 computers all contributing together. So why not use parallel computing to do my calculations? These are called CFD calculations, that is computational fluid dynamic calculations. Today we have got all kinds of fast computers, even some of our laptops are powerful enough, but those days you had these big computers, either mainframes or mini computers, and these calculations were not possible in that. So he built a parallel supercomputer, which later became the model for all supercomputers in India, and even many other countries are developing parallel supercomputers. That was called flow solver. Okay, that was in NAL in Bengaluru, and that was in the late 80s. And later, of course, we developed much higher, bigger and more powerful supercomputers, and which were used. He established, when he became the director of IISc, he developed a climatology center there to do atmospheric sciences and model all kinds of complicated atmospheric phenomena. Another outstanding idea was JRD's idea for establishing TCS. That was in 1968. April 1st, 1968, Tata Sons passed a resolution saying, let us establish a company to do develop computer applications for the Indian economy, to help to increase productivity, help our telephone companies to even print our directories, help our electric supply companies to do billing, to help our universities to do their mark sheets and results, and so on and so forth. Okay, so that was the birth of TCS. And if you want to know the timeline, in 1968, Intel did not exist, Microsoft did not exist, Google did not exist, okay, Siebel did not exist, Oracle did not exist. So you can understand what kind of a pioneering idea it was. There are only two other companies which were doing data processing in the world at that time, which had just come into being. One was in Europe, which now is a forerunner of Capgemini, and the other was in the US called EDS. And so TCS at that time, to think that now we need computers and we need to use applications of computers for the development of our society, our business, and so on and so forth, was a real far-reaching idea which changed so many things. Today, of course, TCS is the largest IT company in the world. Then next is F.C. Kohli. His idea, and then of course an idea needs execution, that goes without saying. It's not just somebody thinking up an idea, bright idea and all that. He needed carrying it through to the end. Was his idea of industrialization of software. Because what programming meant in the 60s was that a brilliant guy who has analytical mind, has knowledge of computer languages, can reduce a problem to a stepwise solution of that problem. Okay, it is called an algorithm. By the way, this should be actually part of our blood, of our DNA, because this method was invented by Aryabhatta and Brahmagupta. That Aryabhatta and Brahmagupta's calculation, the method of calculating, is what an Arabic Persian mathematician called Al-Khwarizmi translated their text into Arabic. And when they were translated into Latin in Europe, they called it algorithmus. This is Al-Khwarizmi's method, and today we call them algorithms. But basically the method is what was developed and explained by Aryabhatta, Brahmagupta, Bhaskara and so on. Okay, but that is what a brilliant programmer does. But the guy sitting next to him doesn't know what shortcuts he has taken, what is the logic he has applied. So if there is any problem to be fixed in that program later, the other guy cannot do it. Or if you say, I'll do half the problem, you do the other half of the problem, they will never work. So in those days, in the 60s, all over the world, programming meant a brilliant programmer, today what we call a coder, solving a problem using a computer and telling the computer how to solve that problem, etc., by writing a program in some language which the computer can process. And that was it. That's no different from what a great a ceramic artist can do, right? He makes a nice pot, or a great painter can do. So it is basically, it was an craftsman's work, it was an artisan's work, because it cannot be standardized, it cannot be repeated, it cannot be distributed, there cannot be any division of labor in it, and so on. Which is what you need for mass production, which is what you need for large scale production. That is, you take a problem, split it into modules, give each module to certain different teams, different individuals, make sure that what they write is in the same style, same standards, and they match each other. And for that also you can develop sub-programs. It is just like what they do in manufacturing, what Henry Ford did. What Henry Ford did, earlier they were making quadricycles. They were called quadricycles, not motors. Same in Michigan and Chicago and all that. They used to make 4 quadricycles or so in a year. He said, can I make an assembly line? Can I make sure that 100 people work on this assembly line and each one does only one part of that job and fixes only one subsystem of that automobile, and the automobile rolls out. And I'll make 100 automobiles in a month instead of making 3 or 4 automobiles. That was the idea of Henry Ford. That revolutionized, that was the manufacturing revolution of the early 20th century. And then later, of course, Toyota made a different just-in-time manufacturing and all that, and revolutionized. That was the second manufacturing revolution of distributed manufacturing and just-in-time manufacturing and so on and so forth. But what Kohli and his associates did in TCS in the 60s and 70s was that can we industrialize software development? So they actually use the concepts of manufacturing, of componentization, of standardization, of quality checks, of distributed modularity in the structure, you know, and all that. And that is how India became, they were able to industrialize software. So that's where a term came into being called software engineering. It was no longer art, it became an engineering. From art it became an engineering, okay, of mass production. And today if India is #1 in the world and everybody and his uncle wants to come to India to set up a software development center, whether it is IBM or PricewaterhouseCoopers or Deloitte or Accenture or Capgemini or anybody, okay, that is because they are finding that talent in India, not because Indians are cheap. Okay, there are many other countries where engineers are cheaper. There are countries which produce more engineers than India also, for example China. Today you have companies in India which have lakhs of software engineers, anywhere from 1.5 lakh to 6.5 lakh in TCS. And the largest software company in China has about 25 to 30,000 engineers. Because they have not yet mastered this management, of industrialization, of project management, and those were the industrialized tools which were developed, and Kohli and his associates like Ramdore, etc. contributed to that, and then of course Narayan Murthy, Azim Premji, and so many, Shiv Nadar, everybody contributed later in the 80s for that work, and that's how today India has the pole position. So that industrialization, it was a great idea, and the execution of that, which is what led to today that being our oil, right? Our oil import bill is about $130 billion, and our software exports is about $150 billion, right? So that is our oil. And if that software and software exports didn't exist, we wouldn't have oil in India. We wouldn't have petrol and diesel or naphtha and gas in India. Next, another great idea was by P.P. Gupta, who was heading a newly formed public sector computer company called CMC. In 1983-84, it was based in Hyderabad. He went to Secunderabad station to book some ticket for his relatives or something like that, niece or somebody, and then he found that he had to wait hours together there for that. And still it was not sure whether he will get a reservation or not. So he said, can we develop a computer program to do this? And then he actually developed it at his own cost, without anybody supporting it, and then went to the railway board and demonstrated it, and mobilized the railway board, and of course Sam Pitoda and Rajiv Gandhi supported it, and that is how computerization of Indian Railways took place in the 80s and early 90s. And that became the biggest ever digital project in the world, okay, by all global standards, till Aadhaar came in. So I'll talk about Aadhaar later. Okay, so then came Nilekani's leadership in Aadhaar, and of course that, and then the RBI's own creation of UPI, which makes digital payments so simple and easy, has revolutionized payments in India, and Aadhaar has revolutionized so many other things. And today, US Federal Reserve is seriously studying how UPI works, how digital payments work in India, because whatever they have done in the US is not so efficient and is not working as well as UPI. And Homi Bhabha's idea of how to use the sand in Kerala beaches to produce energy, which has thorium, and that was the three-stage nuclear program. Okay, let me go to Narendra Singh Kapani. This Sardarji, in 1951, while doing PhD in Imperial College in London, he was in Dehradun, he was an undergraduate. That time he was wondering, can light be bent? See, all laws of optics taught him that light can go in straight lines, right? Rays, we say light ray, reflection, refraction, and so on and so forth. But can light be bent? This was bothering him, and that he took up as his PhD project in Imperial College when he went to London. In 1951, he showed, that was his project, he showed that if you make a glass fiber of a particular type and a particular coating, etc., and particular refractive index, then you can actually, through a bent glass fiber, you can send light. And that was the birth of fiber optics. Okay, there are many things, many people are called father of this and father of that, but basically everybody wants to be father of success, right? Failure doesn't have any fathers. Then they'll say your child to the mother. Okay, but when it comes to gaining credit, they'll say my son did it or my daughter did it, right? So, but in this case, it is genuinely true that Narendra Singh Kapani actually is the father of fiber optics, and he is also the first person to coin the word fiber optics in an article he wrote in 1960 in Scientific American. And at that time, there was no communication, laser communication, optical networking, etc. So what he actually thought of using it is what we do every day in every hospital, called endoscopy. Okay, that how do we look inside the body, inside your stomach, inside every single organ you can think of, and by sending a thin fiber inside your body and with a camera and with a light in it, and so on and so forth. So that was his actually, and he pioneered endoscopy in a sense. Then later, of course, he also pioneered the use of laser for eye surgery in Stanford in the 60s. Fortune magazine in end 99 brought out a special report on people who changed the 20th century. Okay, but unknown people, unsung heroes of 20th century, and he was listed as one of them. Okay, similarly, Arogya Paul Raj, who was I don't know how many have heard of him. He was a naval officer who today has the maximum number of patents on 4G and 5G. He's a distinguished professor in Stanford. He was an officer of the Indian Navy, and he was he's an outstanding engineer, and you can say a genius. Nikhil Jayant, again, he studied in IISc Bengaluru. He and Bell Labs, it is his team which created MP3. Okay, Vishnu Atal, another student of IISc, he thought of a new way of analyzing sound, I mean electromagnetic signals. Earlier people were trying to look at frequencies content of a sound. Okay, how to compress it, how to analyze it, and how can we send it in as thin bandwidth as possible. But they had reached a limit. Then he said, why look at frequency, why not look at amplitude, which nobody had ever thought of. And he developed a special coding algorithm called linear predictive coding, and today every single mobile phone carries a version of that linear predictive coding. That's how your mobile phone works. Otherwise, with thin bit rates, you cannot get clear quality sound. Arun Netrawali, again originally from Karwar, migrated to Mumbai, studied in IIT Bombay, and he later even headed Bell Labs. At Bell Labs, he developed what is today called HDTV. In fact, he demonstrated it in 1984 Los Angeles Olympics. Okay, by putting up screens to show that how this thing can work. And of course, nobody, we don't remember that. We might remember, what is that, Carl's, what is that runner, sprinter who got 4 gold medals, and of course our own PT Usha just missing it by a millisecond or something like that, right? But Netrawali actually demonstrated HDTV in the Los Angeles Olympics. But to come to our homes, it took 20 more years. That shows that technology alone, our product alone is not enough. There is also politics in it. Because there is a political fight between Europe and Japan and United States on what should be the broadcasting standards. And for those things to be settled, it took another 15-20 years. Okay, now let me talk a little bit about design, not much. I said, okay, design is artistic, is all this. So what is design? Because we also talk about design. As techies, we talk about design. Design everywhere, industry, in a chip, in a microchip, design everywhere, right? So I just looked up. Oxford Dictionary, if you look at it, it gives all these definitions of design. And basically, I don't have to tell you all, I mean, you're all either designers or architects and so on, large number of you, right? It continues, a plan or an intention is one of them. And without a plan or an intention, you cannot come out with any solution to any problem, right? Whether it's a product or a solution to a single problem, right? And if you look at the American dictionaries like Webster, and they are much more practical, of course, so they will not talk about design on somebody's wife and so on. Oxford Dictionary will give you all those types of designs, various versions of design, that so-and-so duke had a design on the crown, or so-and-so had a design on some lady, and so on and so forth, right? Which is a different meaning of design. But the Webster Dictionary clearly talks about fashion, execute, construct according to a plan, right? So if I take this aspect of design and not the aesthetic aspects of design, then of course engineers and techies have something to say about design, because without that you can't come out with any product or even any service. And interestingly, when JRD Tata established the first research center which was attached to TCS in 1981, when at that time none of the technology companies, Microsoft or anybody, had any R&D center. At that time he established an R&D center in Pune. He didn't call it R&D center. He called it Tata Research Development and Design Center for a specific reason. Because without design you cannot even write software. And that's how these words, and when it celebrated Silver Jubilee, I edited a book for TCS. That time I was working in TCS, called Research by Design. Of course I used a different meaning of design. That is, with a plan, research with a plan, because industrial research is not a blue sky research. Right? It's not that you can find anything interesting and work in that. But you need a plan, you need a business outcome out of it, you need an industrial application out of it. That's why I called the book Research by Design, which was actually on the Silver Jubilee of our R&D and Design Center, and that book was released by President Kalam in 2007. And you see these terminologies which are used in the IT industry: software architect, computer architect. Okay, computer architecture, all the IT students will know. Von Neumann's architecture, how, all these computers are based on Von Neumann's architecture. Systems approach. Okay, what are the different parts of a system, what is the interaction between the parts, what is the relationship of the part with the whole, how does a subsystem interact with its environment, all these things. So while designing anything, all these things have to be taken into account, including software, okay, or any other system. And based on this approach only, very interestingly, using even cognitive studies, that TCS came out with a software and distributed it freely, so that any adult, illiterate adult, can learn any language within 40 hours. And that was called CBFL, Computer Based Functional Literacy Module. Okay, so these are just some examples. Now I have some questions for architects. Okay, like the famous rock cut temples. They are in many parts of Maharashtra: Mahad, Nasik, Lonavala, Karla, etc. Right? Nasik is the one. Okay. Right. So anyway, so these rock cut temples were built from 1st century BC to 5th century AD. They are called Pandava caves. Basically, they are Buddhist temples. Okay. Now the point is, when we look at any of our monuments, and I've asked many historians and archaeologists, what do they tell me? They tell me which century, which date, who funded it, who was the patron, and who built it at the most, who was the master craftsman or the architect who did it. But they don't tell me how it was built. In 1st century BC, how did they cut that hard rock? What were the metallurgical tools they used? What was the engineering technology they used? Nobody tells me. I want answers. I want people to work on this and tell people like us what was the technology involved in building our monuments. Same thing with Qutub Minar. What is amazing about Qutub Minar is not that it is 7 centuries old, but being in seismic zone for 7 centuries, it has not fallen or cracked. Our house is built with RCC, cracked with every earthquake. And we say we want to learn earthquake engineering from the Japanese. Right? Same thing with Taj Mahal. When I went to Taj Mahal, at least my eyes, I saw that if you look at the minarets, they have a conical structure. And they are made of C sections of marble. Right? And that means the C is not perfect cylinder, it is actually part of a cone. That is how it tapers. So that perfect buffing, that perfect engineering, how was it done? On top of it, it is marble, which is so brittle. And it has been around for 300 years. And how many earthquakes have happened in the Himalayas nearby? How come it has not cracked and fallen? What was the foundation engineering used in Taj Mahal and in Qutub Minar? Nobody has told me so far. People tell me who was the architect, was it an Albanian, Khorasani, Persian, who, etc., etc., okay? And who were the other people who worked on it? Or how Shah Jahan funded it, etc. So these are some of the questions I have. I want some answers for that. Now, of course, there is a whole field called archaeometallurgy, where leading metallurgists in India have worked on it to reverse engineer some of our marvels, like the Iron Pillar or the Chola bronzes, and see what was the engineering involved in it. Okay? That's it. Now all I'll do is to add a little bit of color. I know I'm told that many of you are waiting to fly away, so I'll just flash some photographs to you to add color to this. This was the book I edited for TCS, Research by Design. This is TRDDC, one aspect of it, Tata Research Development and Design Center in Pune. JRD, of course. This is P.P. Gupta, who actually computerized Indian Railways. Nandan Nilekani, of course, you have seen him every other day in Bengaluru, right? Aadhaar and UPI. This is Arun Netrawali, who was, you can say, headed the team which built HDTV. This is Nikhil Jayant, who created the technology for MP3 at Bell Labs. His actual name is Nugihalli Jayant, by the way. He comes from Nugihalli. But when people go to US, they tend to change, right? So he became Nikhil from Nugihalli Jayant. This is our Sardarji in 1951 in the lab in Imperial College, experimenting on fiber optics. This is Professor Narasimhan, who created the first digital computer in 1954 in TIFR. This is F.C. Kohli, who industrialized software and created all kinds of other things, including that giveaway free software to teach any adult any language within 40 hours. Ram Dorai again, who worked with him in software engineering. This is Arogyasamy Paul Raj, outside in the Stanford campus, who created all these wonderful technologies for 4G and 5G. Basic technology, which is called MIMO, multiple input, multiple output. It is also called space-time multiplexing. Sam Pitroda, outside his house in Chicago, who laid the foundation of telecom revolution. Vishnu Atal, who was telling you about, created that linear predictive coding, which is in all your mobile phones. This I didn't mention him, Bala Manian. He is actually mechanical engineer turned optics engineer, and he created the technology to transfer film, digitize a film for medical purposes. How can X-ray film, if I want to send the X-ray film content to another doctor anywhere else? Okay, so for medical engineering purposes, he devised how to digitize a film, send it through old telephone network to there, and then convert that, print it back into a film, and that guy will see it, consultant will see it and call you back. Right? Today we call, this was in 72, 73. And later, Pixar and George Lucas, Industrial Light and Magic, picked up his patents and his technology and created computer graphics for Hollywood. That's why he was probably the first Indian to get an Oscar. In '99, he was given technical Oscar for his contribution to digital cinematography for Hollywood. Thank you.